Hello, for today's video lecture we're going to be looking at polar area moments of inertia and specifically calculating those via the second moment integral. So first we want to talk about why these things are useful in engineering mechanics, and that comes down to the concept of torsion. So what we usually call the polar area moment of inertia, which we abbreviate as J, is going to be the second polar area moment integral for a shape. And in this case, it's going to be the cross-section of some shaft we're subjecting to torsion. So this value is useful because it offers a quantitative measure of a shape's resistance to torsion. And so the bigger the value of J, the more resistant it is to torsion. And that helps us, this quantitative measure helps us relate torsional loads. So this would be the torque we apply to some shaft to the shearing stresses, the torsional shearing stresses we experience within that shaft. So the diagram above shows a torque applied to a shaft and the resulting internal stresses. So I've got some torque, I'm twisting on this end of the shaft, this side is fixed, and so it's going to experience some internal stresses. And all of these are shearing stresses here. So we are using the second moment integral as a measure of the shape's resistance to torsion, because we need to sum all of the moments that each of these little pieces are exerting that can counteract this torsion on this side, because the whole thing is going to be in equilibrium. So this goes up by a factor of 2 because, number one, as we move out from the neutral axis where we have zero stress, we are looking at the moments, or summing up the moments that this kind of internal stresses exert. And so the moment is force times distance. As I move up, distance increases, but also you can notice on the diagram that the force also increases linearly with that kind of separation. And I've got this drawing here is as we're going up or down, but it's going to be the same kind of process if I go left or right. So force increases with distance, distance increases with distance, and so resistance to bending increases with distance squared. All right, so how would I go about calculating this? Well, we start with the equation for the second area moment integral. If I'm integrating over some area, I've got this d squared term, that's the second area moment integral. All right, and I need to think about what that distance is here. And so in this equation, we're going to be moving out from some axis, and that neutral axis in a shaft, or due to a torsion, is actually going to be, if I'm looking at the cross section of the shaft, it's going to be the z-axis. So it's pointing kind of directly out towards you, and it's really going to look like a point in a 2D cross section. And so I'm moving out from some point, that's the origin point, and that distance is the distance from the origin. So generally, we're going to make it so that the centroid of my shaft is the origin point, and as I move out from the origin point, I'm going to look at that value for what I'm going to call r. All right, so because the neutral axis is the z-axis, we're going to abbreviate the moment of inertia, or the polar moment of inertia, as J, and sometimes you'll see JZZ, indicating that we're moving out from the z-axis. So for the distances, we're moving out from this central point in a circular pattern. So everything that is r away is going to be some circle that is r distant from the central point. So we've got this radius, that's why we're going to use r, and our equation here, going from some minimum r value to some maximum r value, we're looking at r squared for our distance. All right, so we're going to go a little bit further and look at a diagram here. So I've got a circular shaft, and if I want to find JZZ, the moment of inertia about the neutral axis, or the center point right here, I'm going to go start at our minimum. In this case, I've got material there at the center. So it's going to be 0 out to the maximum radius, the outer radius of my circular shaft, and I'm integrating dA times r squared. So dA is the rate at which the area is changing for this piece. And so if I think about starting in the center and moving out, I want to find the area of this little sliver at some value r, small r here. So If I've got a complete circle, that small area, it'd be simply the circumference, and the width of this little sliver of circle would be dr. And so the circumference is 2 pi r times dr for this complete circle. But I also need to consider if I've got something that's not a complete circle going around, it's not going to be 2 pi r, it'll be some fraction of 2 pi r. So maybe I've got some cutout that takes out part of that circumference. So dA is the equation describing the circumference of the circle with radius r within the shape, times the rate at which the radius is changing, which is dr. I take whatever that equation is, as I move out, I multiply that by r squared, and I integrate that from some minimum radius to some maximum radius. And that, if I have all numbers, and I've got some like physical system to be working with, I'm going to wind up with the moment of inertia about the neutral axis, which is a quantitative measure of this kind of cross-section of the shaft's resistance to torsional loading. All right, so with that, that's all I have for today's video lecture. Thank you for watching, and I hope to see you again.